that. So I was talking about semiconductor lasers. So I stopped on this slide, which shows the spectral coverage of various types of semiconductor lasers. So you can see here different compounds of semiconductors and their the corresponding wavelengths. So you can see that these semiconductor lasers cover a very broad range of wavelengths, ranging from the visible, so violet, up to the even mid-infrared, with different compositions of the semiconductor. So now maybe a few words about the cavities and resonators that are used in semiconductor lasers. So generally, all they are based on Fabry-Perot cavities. Maybe not every semiconductor laser, but most of the lasers, semiconductor lasers, are based on Fabry-Perot cavities in some different configurations. So we distinguish so-called distributed feedback, DFB laser, distributed Bragg reflector, DBR laser, a grating stabilized light laser, and ECLs stand for external cavity lasers. And I will briefly describe all these types of resonators. And they are, of course, Fabry-Perot resonators, but some kind of modifications of Fabry-Perot resonators. So the DFB laser, the distributed feedback laser, this is one of the most commonly used configurations in fiber lasers, which are used in telecommunications, for example. So these lasers are used as so-called as signal lasers, right? So they are used for not only telecom, but any other applications where you just need a low power laser for generating a stable signal that you want to modulate or encode some information into the signal. So the main principle of this resonator is that there are no mirrors, basically, but the mirror is formed by the difference between the refractive indices of the materials that are used here, because the semiconductor will have a high index, let's say at the level of maybe even 4, and the index of air is at the level of 1, right? So the reflectivity of such a border between the semiconductor and the and atmospheric air will be at the level of maybe even 40% roughly. So this is the mirror. And inside the structure of the laser, we have a so-called Bragg grating incorporated inside the structure. So the Bragg grating is a grating of the refractive index of the material. So the material, the semiconductor, is prepared in a way that the refractive index is slightly modulated along the optical axis, right? So we have areas where we have a higher index and a lower index, a higher index, lower index, right? So we have something like that. So this is how the structure of the index looks like over the along the laser, and the difference is of course really small. So it's at the third, even fourth digit after the comma, right? So we have like 4 point something and 4 point, let's say 000, and you have 4.00 maybe 2, something like that. So it's a really tiny change of the index. And this kind of structure will act as a mirror for a specific wavelength, depending on the length of this period. If this period of this index change equals lambda 1/4 of the lambda, then this kind of structure will act as a reflector for the wavelength of lambda. So the reflectivity of such a mirror as a function of the wavelength will look like that. So we have some peak reflectivity. We have some central wavelength, which will be lambda. and we have some bandwidth, and we have some ripples here. So we have some suppression of these ripples. So this lambda corresponds to the period of this modulation, and the reflectivity will be proportional to the to this modulation depth of this index. So if such a grating is incorporated in this diode structure itself, it means that only wavelengths from this band will be existing in this resonator, right? So we will have only one selected wavelength, or one very narrow range of wavelengths that are existing in this kind of structure. So this laser will be just intrinsically a single frequency, so single longitudinal mode over a very broad range of temperatures and currents. And it enables also a little bit of tuning of this central wavelength, because if we change the temperature of this structure, we will change the size of this grating, right? So we will change this lambda here, the period of this index change. So by that, we are just moving around this central peak wavelength of the reflectivity. So by doing that, we can slightly tune the wavelength of the laser. So this is a DFB. Something slightly different can be done with a so-called DBR, which is distributed back reflector, which means that the reflector is outside the active region of the diode. So we have the active region is limited here, right? So we have the gain medium here, and the grating is kind of a separate part of a semiconductor, which is, it might be directly bonded with the structure or just directly grown in the same process, but it's a kind of a separate component here. So we have this grating reflector. So on one end, we have just the reflectivity from the border between two different reflective indices. And on the other hand, we have the reflection from this grating, from this Bragg mirror. And here what we achieve here is a slightly broader tuning range, because we can selectively heat only this part of the structure. So we can change the size only of the mirror. So we can elongate this this grating. So by that we can tune the reflectivity, tune the wavelength that is reflected by this mirror. And we don't have to heat up the entire active region, but only the grating. Another option is to use a grating only for stabilization of lasers. So again, we have just a Fabry-Perot cavity. So this is one mirror here. The second mirror is here. We have no grating inside the laser. This is just a Fabry-Perot resonator. But we have a reflective grating outside the resonator. So what this grating is doing is that it is reflecting a tiny portion of light, which is then injected back to the laser. So it acts as a kind of a seed for the stimulated emission. So this wavelength is stabilizing the emission. This grating is stabilizing the emission wavelength of the laser. So it is not a laser mirror. It just provides a very small feedback to the laser to stabilize the wavelength. And this is also a Bragg grating. And this kind of grating can be placed on a fiber. So if we have a laser that is coupled with a fiber, so we have the laser and we have a fiber, and here we have the output of the laser. So this grating can be placed somewhere on this fiber because it's easy to fabricate gratings on fibers. And then a very tiny portion of the light is reflected from the grating and is going back to the laser, and the main part is of course transmitted through the grating and goes to the output. But we have a very small positive feedback here, like maybe, I don't know, 1% or even less than 1%. And the fourth option is a external cavity laser. So this is a laser in which we have one mirror just somewhere on the back of the structure, and the second mirror is just a external mirror which is just separately placed somewhere at a given distance from the structure. And in this case, we can place, for example, a grating, just a diffraction grating inside the laser, and a diffraction grating is reflecting different wavelengths under different angles. So it means that if we rotate the grating, we can just select wavelengths that can be that can exist in this resonator, because if we place this grating as at a certain angle here, then all the wavelengths that could be generated in this laser, they will be just reflected in under very different angles, and only one wavelength will be reflected in a way that it will be then directed back to the structure. So by that, we can select the wavelength, and if we rotate the grating, we can just tune the wavelength of our laser. So this enables very broadband wavelength tuning. And the line widths are quite narrow because the grating can select a very tiny portion of the spectrum. However, of course, this is a bulk construction, so it is not integrated because we need a rotating grating. So this is usually a quite large instrument. And there is a huge group of lasers that are called surface emitting lasers. So last week I was showing you the so-called edge emitting lasers, where we have two pieces of the semiconductor joined together, and we have the active region, which is here on the border between the two types of the semiconductor, right? So this was the edge emitting laser. But one can make a surface emitting laser. So instead of using the edge, we can force the laser to operate in this perpendicular direction. So we just make a hole in the structure on the top, and we make a reflector on the bottom. And this is shown here. So we have this aperture here. So the active region is visible here in the red, and we have a reflector on the bottom. So we have a lower here Bragg reflector in this case, right? So we can have Bragg reflectors. And these lasers have smaller sizes because the length of the resonator is very small, just few micrometers. And if the volume is smaller, then we have smaller capacities, then we can have higher modulation frequencies. So these VCSELs, because these are called VCSELs, so vertical cavity surface emitting laser. These lasers can be modulated with really high speed, and usually they are used in telecom. So nowadays they are using VCSELs at the wavelength of 1300 nanometers for telecommunications. And a kind of a modification of the vertical cavity laser is a vertical external cavity surface emitting laser. So this is basically the same the same thing as the ECL that I was showing you 3 slides ago. So this is just a VCSEL, so a vertical cavity laser with a separate mirror. So by doing that, we have just a free space segment where we can just an air gap where you can put some elements inside. So for example, we can put a diffraction grating inside, or filters, or any other functional components that we would like to have here, right? So semiconductor lasers can be found in different housings. So since you are engineers, I thought that it would be worth to show you how this looks like. So usually they are packed in standard TO cans. So we have just some pins and just the output window where the light is extracted from the laser. There are, as you can see, many pinouts, standards. So before connecting each laser, you need to check what kind of structure you have. As you can see, there is not only the laser diode inside, but there is usually also a photodiode inside. So the photodiode is used for just monitoring of the output power of the laser. So you can just have a feedback and monitor whether your laser is working fine. So these lasers, these TO lasers, are usually low power lasers. If we have higher power lasers, they can be mounted in so-called C mounts. So you have these kind of copper heat sinks, and the structure of the diode is placed here. And this is also inserted in a bigger mount with heat sinks and connection to the power supply. If the laser is coupled with the fiber, then usually we have so-called butterfly housings. So this is a 14-pin butterfly housing, a very typical common housing. So if you buy a laser coupled with the fiber, then most likely this will be a butterfly laser. So in this butterfly housing, we have the entire optics that is used for coupling of the light from the laser to the fiber. So the laser is somewhere here, and then we have some collimation optics, sometimes also an isolator that prevents the laser from damage because of some back reflections. So we have these optics, and then this is launched into the fiber. We have also a thermoelectric cooler. This is usually a Peltier element. So this is just a component that allows us for easy cooling of the component. So then we just put this mount, this diode on some heatsink, and we extract heat. Of course, there is some also a monitoring photodiode inside as well. So if you look at the pinouts, there are two standards. One standard applied to so-called pump lasers, so lasers that emit higher powers, and type 2 for signal lasers, which are low power lasers. So always before you connect a butterfly laser, you need to make sure which type you have. And you can see that, yeah, there is the laser diode. We have the thermistor to monitor the temperature. We have the thermoelectric cooler, and the monitor photodiode. And some of the pins are unused. So very recently, some of the manufacturers also developed a 10-pin butterfly, because here we have 4 pins that are actually might not be used. What is important about fiber-coupled lasers with semiconductor lasers with fibers is that these diodes might be coupled with a single mode or a multi-mode fiber. Okay, so in general, the fiber type that we are connecting, so either this is the single mode or multi-mode, it limits the available output power. So if we want to have a single mode fiber at the output, so single mode means that we will have a beam like that. So we will have a very nice round beam with the TM00 mode, a very clean Gaussian distribution. So this is a single mode fiber. We unfortunately limit the output power of this kind of diodes. So usually they are available with powers up to maybe 1 watt. But if we don't care about the beam quality and we just agree with a very multi-mode transverse mode operation, then we can have even hundreds of watts coupled into one fiber. So if the fibers are multimode and they have large cores like 200 or 400 micrometers, then you can couple hundreds of or even kilowatts of power into one fiber and have a multimode beam, but extremely powerful. So few words about how we drive these diodes. So what we basically need to operate a semiconductor laser is a stable current source. A stable current source for driving the current of the diode and also driving the current of the thermoelectric cooler if it is integrated in the laser. So there are many devices available on the market, so you can just buy kind of a tabletop instruments that just have a touch screen, and they just enable you to set the current, set the temperature, and read out the voltage or the power of the laser and the temperature and so on. And they are available up to 20 amps. It's very easy, but even sometimes to 50 or even more amperes. There are some modules that are enabling some integration. So if you want to build your own laser diode driver, you can either build your own current source or just use commercially available packaged current sources. So for example, the Torlabs one gives a current at the level of 200 milliamps, 3 volts voltage, so-called soft start. Soft start means that the current is turned on with a ramp, with a slope. So over time, the current is not rapidly growing, but to avoid some overshoot, but just is we have just applied a ramp to avoid this overshooting. Or the wavelength electronics FL500 is an example of a 500 milliamp chip with 2 volt voltage, also soft start, and it enables also amplitude modulation of the current. So this is miniaturized, as you can see. What you just need is just to connect some capacitors, some resistors around, and just connect the voltage and connect the diode, and that's all to make the driver. And the cost of this is, I don't know, maybe this one costs like I'd say maybe $50 US dollars, of course. Okay, do you have any questions regarding the semiconductor laser part? Yeah, if not, then I will move on to the description of the next type of laser that we will discuss. So these are the solid state lasers. And on the next lecture, you will say a little bit about pulsed laser, and this will be all from my side. So solid state lasers are, as you can guess from the name, these are just lasers that are based on some kind of solid material, like crystals, like glasses, or also fibers. So in generally, this works in a way that we have some doping, some impurities, some dopants in the solid state material, which is dielectric, which we call a host material. So we have a host, and it is doped with some ions, right? So some ions of some elements. And an example is a YAG crystal, which is the yttrium aluminum garnet, which is doped with the neodymium ions. So we write it as you can see here. So this is the way we write the names of these lasers. And these dopants here might be either lanthanides, which are so-called rare earth ions, or also transition metal ions. So this might be any ion that has the possibility to absorb light and has proper transitions and can emit light. So there are several examples of lasers, laser host materials, and dopants. In general, the number of dopants that can be used in lasers is limited because we already know all the dopants that you can use, and probably there will be no new elements that will be that could be used in lasers. However, people still invent different host materials. So these host crystals, host glasses, are constantly under development. So if you open a scientific journal about optical materials, you can read every day new reports about new kind of crystals or just host glasses that can be used for making lasers, because people still want to improve the, for example, thermal conductivity, transparency of the material, or just the ability of incorporating these dopants with high concentrations. So the most popular solid-state laser is the neodymium YAG or neodymium EVO. So these are lasers based on yttrium aluminum garnet or yttrium orthovanadate doped with neodymium. But there are, of course, many other options. So as you can see, they can be just based on glass, or for example, based on sapphire crystal, and many other types of crystals. So today I think I will describe the neodymium-based lasers and also the titanium sapphire laser. And I think that would be all for today. So this slide shows you the most typical dopants that can be used in lasers, in solid-state lasers, and I have written the corresponding emission wavelengths and pump wavelengths that are used to pump these lasers, because solid-state lasers are lasers which are pumped optically. So it means that we have our solid-state laser. So this is, let's say, our Fabry-Perot resonator. So we just put between these two mirrors, we just placed our crystal, right? So in gas laser, this was just a tube filled with the gas. Here, this is a crystal which is doped with one of these ions listed here. So if we want to emit light from this kind of laser, we need to pump it. So we pump solid-state lasers with another laser. So we need to use another laser, a pump laser, that will just pump our crystal optically at a wavelength of, let's say, lambda pump, and the laser will emit the wavelength of lambda EM, which stands for emission wavelength, right? So here you have grouped the possible ions. So we have the 5 ions here. These are the lanthanides, so rare earth ions, and these here are metals. So we can dope either with lanthanides or also transition metals. So the most common one is neodymium. Neodymium has the emission wavelength at 1064 nanometers, and we need to pump it at 808 nanometers. So when we excite our crystal with the wavelength of 808 nanometers, we will we will have emission at the wavelength of 1064 nanometers. And for that, we can use either a diode laser, a semiconductor laser, or we can also use a flash lamp that can deliver this wavelength. Second one is holmium. Holmium has a broad emission bandwidth from approximately 2000 to 2200 nanometers. And for pumping, we can use a band at 1100 or 1950 nanometers. So the 1950 can originate from a thulium doped laser, or the 1100 can originate from a diode. Erbium doped lasers, these are also very popular lasers. So erbium doped lasers can emit at the range between 1530 to 1600, and also there is a mid-infrared transition at the wavelength slightly below 3 micrometers, and these lasers can be pumped at around 976 or 1480. Yeah, and the same applies to thulium, ytterbium, and so on. So I will not read it. So you can you will have the presentation, so you will see it. But it is important to remember that there are some certain absorption bands in every ion where you can pump the laser, but there's always an absorption peak where you have the optimum pump wavelength. So these optimum pumping wavelengths are listed here, and it's good to remember which laser is emitting at which wavelength and which pump is corresponding to which laser, and so on. Maybe it's only good to mention that the titanium sapphire laser requires a wavelength of 532 nanometers, which can be achieved with a solid state laser with so-called second harmonic generation. I will also mention a few words about that today. So this is just a usually we use a neodymium laser, which is 1064, but in some nonlinear process, we can just divide the wavelength of the laser by 2. So we just divide the wavelength by 2, and we have 532, and we can pump a titanium laser because then we have the second harmonic. So we have 532. You can also see that, for example, the absorption of the thulium laser here matches with the emission of the erbium doped laser. So it means that we can use an erbium laser to pump a thulium laser. And if you look even further, you will see that the absorption of holmium matches with the emission of thulium, because this is 1950, which is also covered by the thulium. So the thulium laser can be used as a pump for the holmium. So it means that sometimes we build kind of cascades, because the thulium laser emits the wavelength of, let's say, 2020 nanometers, and we use holmium, and we use a thulium laser to pump this holmium laser, and we use an erbium laser to pump the thulium, and we use a semiconductor diode to pump the erbium. So we need to follow like 3 steps of conversion of wavelengths to get the final wavelength. So sometimes these constructions start to be quite complicated. Yeah, so you will have this slide, but I recommend to remember the wavelengths that are emitted by these lasers and the pumping wavelengths that are needed to pump them. Okay, so historically, the first solid state laser and simultaneously the first laser ever was a ruby laser. So this was the ruby crystal. You might know that ruby is used for jewelry. So I assume women know a little bit more about that. But generally, ruby can be used also in optics. and also for making lasers. So the structure of the setup of the first ruby laser was very simple. So there was just a ruby rod and just two mirrors which were just attached to this ruby rod, and there was a flash lamp used for pumping of this ruby rod. So the energy was delivered to the ruby atoms from the flash lamp. So this is how it looks like in the 3D image. So there were two mirrors. So this is the mirror here, and the second mirror is here. The ruby rod is placed here inside, and the ruby rod is placed inside this kind of a spiral flash tube that delivers light to the flash lamp. And the housing for that was coated with metal here inside, so that the light emitted from the flash tube was also reflected by this inner surface of this housing and directed once again to the ruby rod. And the ruby laser was emitting the wavelength of 694 nanometers. These are the pictures of the first ruby laser, which was done by Theodor Maiman. So you can see the rod, also the lamp, and the entire housing. So this is Theodor Maiman holding his laser. So it was the first working laser. It was working only in the pulsed regime in this case. So this was just a synthetic ruby crystal, which was formed as a rod with some few millimeters of diameter and few centimeters of length. And it is not so often used today. So it's rather, you can rather find ruby lasers in the museum instead of laboratories, because this is a 3-level energetic system. So as we know already, the 3-level system is not so effective because we need to have population inversion between the upper laser level and the ground state. So this is the simplified energy diagram. So the chromium ions absorb the, let's say, blue portion of the light emitted by the flash lamp, and depending on the configuration, we can excite either the level T1 or T2. Then we have a non-radiative decay, and we have two possible lines, R1, R2, at two different wavelengths that can be emitted from this ruby laser. So this is a very simple structure. And yeah, this was the first laser. However, as I said, the probably most popular and most commonly used laser is the neodymium doped laser. It is very often used in the industry, and neodymium can be used in combination with YAG, which is the yttrium aluminium garnet. Here you can see the composition, or yttrium orthovanadite, which is EVO 4. I will say about EVO a little bit later. And these lasers can be also pumped with lamps or with diodes. So diode pumping is much better than lamp pumping. I will explain it also in a minute. These lasers are suitable for high powers, and neodymium lasers are purely 4-level systems. So typically they emit the wavelength of 1064, and the peak absorption is at the level of 808 nanometers. And this is very often frequency doubled. As I said, we can double the frequency of this light, and the optical to optical efficiency of this kind of lasers often reaches 50%. So they are quite efficient. So this is the absorption spectrum of neodymium. So if you look at this spectrum, you will see that there are many absorption bands with very intense pronounced peaks at around 800 nanometers. That's why we use lasers at 808 nanometers to pump neodymium. Yeah, the system is purely 4-level. So this is the simplified 4-level system. Just just to remind you about what the 4-level system is. So we just pump this upper 2nd level. We have some non-radiative transfer. Then we have the emission of light between the levels 3 and 4. And then once again, we have some kind of decay to the ground state. And if we look at that in more detail, there are, of course, many more transitions that are possible in neodymium ions. So we have many lines that can be used to achieve radiation at different wavelengths. So the 1064, the most intense one, is just one of the lines, but there are examples of neodymium lasers working at other wavelengths as well, right? And also this way. But as I said, the most popular one is the 1064 nanometer wavelength. Yeah, some basic parameters of neodymium, but what is the most important? Yeah, the index of refraction 1.8, so slightly bigger than typical optical glass. Yeah, I think nothing important here. So these neodymium crystals are grown in usually the standard Czochralski process. So you see this is the bare undoped YAG. This is YAG doped with neodymium. So it changes the color to kind of purple color. And you can buy these crystals in the form of either of a rod or just small, tiny bulk pieces of crystals, even discs, depending on your application. And this is easily available on the market in different sizes and shapes. So depending on the application, you can choose over a variety of sizes and shapes of the crystals. So as we already said, the laser can be pumped either with flash lamps or diodes. So if you use flash lamps, then it's important to make sure that you can make an arrangement to focus as much as possible of the light from the lamp into your rod. So that's why these rods, these flash lamps are formed in the way that they just surround the rod, and then you also put some reflective reflectors on around this system, so that the light that is emitted by the lamp is emitted in any direction. So then it is reflected from the walls of this housing, and they can be reflected back and hit the rod. So for that, people also use different geometries, like kind of elliptical structures, where you have the rod and the lamp placed in the other focal point of this ellipse, or one rod and kind of a double elliptical shape, where we have 4 lamps and 1 rod. And due to this elliptical shape, the lamp from the rod, it will be always, the light from the rod will be always reflected, so that it will be focused in the rod. However, the way more efficient way of pumping of solid state laser is the pumping with laser diodes. Okay, so you already know that we have a variety of semiconductor lasers at many different wavelengths and many different powers, right? We can easily achieve high powers at a very broad range of wavelengths. So the more efficient way is just to use a laser diode, because we can target just a specific absorption line of the crystal instead of emitting a very broad spectrum from the flash lamp. Okay, I think I have it somewhere on the slide. So if we compare the flash lamp pumping with diode pumping, you will see that the flash lamp covers a very broad range of wavelengths, right? Because the flash lamp is just the white light, okay? So the white light contains spectrum from the entire bandwidth of the visible and the near infrared radiation. So as you can see, a lot of energy from the flash lamp is just wasted because we have no absorption here. So we basically don't care about the power of our lamp here. So instead, we can just use a laser which has a narrow bandwidth, so we can perfectly target one absorption line of the neodymium ion, and we can just focus a lot of power to have much more absorption, because the absorption coefficient here is much higher than on other lines that could be excited with the flash lamp. So diode pumping is much more efficient. And also diode pumping can be done in many different ways. So one of the pumping schemes is so-called end pumping. So end pumping means that we pump we pump the crystal from one of the ends. So you can see it on the example here. So we have our neodymium crystal. So this is the neodymium yak crystal here. The crystal is placed in a resonator. So we have two mirrors. First mirror here, and the second mirror here. And this first mirror needs to have characteristics so it transmits 808 nanometers. So this is high. HT means high transmission, and HR means high reflectivity. So it means that if we take our 808 nanometer laser, it might be a fiber coupled laser or not necessarily, it doesn't matter. We just use some optics to focus the light on our crystal here. And the 808 nanometer light is easily transmitted through this mirror because we have this HT coating on the mirror. So when you focus the light on the yak crystal, it absorbs light, 808 light. Okay, so we excite our upper level by pumping of 808 nanometers. Then we will have some non-radiative decay, and we will have emission at the wavelength of 1064 from the upper laser level. Okay. So again, we start with spontaneous emission, and then it will turn into a stimulated emission. And the emitted photons will have the wavelength of 1064 here, shown in blue. And this back mirror has also reflectivity of 90% at around 90% at 1064, which means that the wavelength will be reflected and 10% will be extracted. So this will be our laser output, and the rest will just still be amplified in the resonator. So this is called end pumping because we pump from one end. So the end pump lasers might have different configurations. So for example, one mirror can be directly deposited on the crystal. So we have the crystal here, and you can see that one of the mirrors is directly deposited as a layer on the crystal. So you can just take the crystal, to the coating machine, and we can just put the coating on one side of the crystal. And we can also do it on both sides of the crystal, which is shown here. So we just take the crystal and we just deposit layers, reflective layers on both ends of the crystal. And by doing that, we can build a so-called micro laser, because the entire resonator is here. So this is just closed between these two mirrors. So we have no free space, separate resonator, but it is just deposited directly on the crystal. In case of high power lasers, we need sometimes to use more than one laser diode for pumping. So in this case, it is also important to find a way to couple all these laser diodes into the neodymium crystal or neodymium rod. So in this case, we can use also arrays of diodes, which are arranged in the way that they are placed next to each other, and we have the rod inside. So each of these diode arrays is just shining on the rod, right? And if you look at it from that side, at the cross section of that, you will see that the rod is here, and these diodes are just surrounding this rod, and each of these lasers is just shooting into the rod from each side. So it means that the rod is just surrounded by lasers, which are just shooting with light, and the rod is absorbing the light from these diodes, and it is emitting laser light in this direction. The typical optical to optical efficiency, so optical to optical means how much pump at 808 we launch into the laser and how much power at the wavelength of 1064 we get from the laser. So typically it reaches around 50%, right? So it's a quite high efficiency, but you need to remember that 50% means, so we have our neodymium crystal and we have our pump. So it means that if I launch, let's say 10 watts to the crystal, I will get 5 watts at the output of my neodymium laser, but I need to deliver at least 20 watts to my pumping laser. So the wall plug efficiency will be a little bit less, right? So this will be about 25%. However, this is still a very high efficiency if we compare it to the efficiency of the gas laser, for example. And then some other configurations of pumping of rods. So you can see different arrangements. So like 3 lasers that are pumping the rod. Yeah, this is something I already told you. And the next host that can be used in neodymium laser is the EVO crystal. So the EVO is yttrium vanadate. What is important? What is the difference between EVO and YAG is that EVO will have a slightly larger pump absorption, and it is a little bit better for pulse operation, but maybe a bit worse for high power lasers because of the shorter upper laser lifetime, upper state lifetime. So, but generally it's more or less the same as the EVO. It's just a different host. So it also can be found on the market in different forms, different shapes, different doping concentration, and so on and so on. This is an example of a micro laser, microchip laser with deposited mirrors, so you can see how small the laser can actually be. And what is important in neodymium doped lasers is, I already mentioned about that, they are really suitable for so-called generation process, SHG. So this is the process of frequency doubling of light. So it means that there exist nonlinear media, solid state media, which have the possibility to double the frequency of light. So if we shine on something like that on this nonlinear medium, a wave at the frequency of omega, so at the output, we will get a frequency of 2 omega, so doubled the frequency. And of course, some residual omega, which was not converted, because we don't have 100% of conversion efficiency. So it means that if this is lambda, I will have half of the lambda at the output. So ideally, if we use a 1064 laser that can originate from a neodymium laser, we can get green emission at 532. And you might already know that this is the principle of these green laser pointers that you can buy. So these are just neodymium lasers with second harmonic generation. So if we look at the internal structure of this kind of laser pointer, we will have the neodymium crystal. So this is usually neodymium Evo 4. This crystal has mirrors deposited directly on the surface. So you have 2 mirrors, M1 and M2. We have a semiconductor laser here. So this is a semiconductor laser at the wavelength of 808 nanometers. So it, let's say, emits light here at 808. The neodymium laser is emitting 1064 nanometers. And then we have the crystal for second harmonic. So this is usually a lithium niobate crystal, but it doesn't matter for now. But a crystal that converts this, the color. And then we will have 532 nanometers, which is green. And all that is also power supplied with a battery, right? So we have a battery that is just powering our semiconductor laser. And this is packed in the housing of a laser pointer, right? So it looks like a pen. And you can buy it for, I don't know, maybe 50 zloty, right? On eBay or anywhere else. So as you can see, how many components we have inside. So we have a semiconductor laser, we have a crystal with mirrors, and we have a nonlinear optical process. So you have another crystal that converts the radiation, and we have the green emission, and this costs almost nothing. So it just shows you how laser technology is advanced nowadays. Okay, I will go back to the presentation. Okay, so now I'll move on to the second, not just the second, I mean, maybe next, third laser that I'd like to describe. So this is the titanium sapphire laser. So titanium sapphire is an example of a laser which is not a lanthanide-based laser because this is doped with a metal, right? So this is titanium, and this is the sapphire crystal. And the main property of titanium sapphire laser is the fact that it has a very large gain bandwidth. So it means that the laser can emit light from any of these wavelengths shown here. So this is an extremely broad wavelength range between 650, maybe 700 nanometers up to 1100 nanometers. It is also very good for high power lasers because it has an excellent thermal conductivity. So it is very easy to extract heat from the titanium sapphire laser. And last week when I was on a conference, one group from Korea, they have shown a titanium sapphire laser together with some, of course, amplification stages that were emitting the power of 4 petawatts. So this was basically the highest intensity ever recorded, because you can imagine that the petawatt is quite a high power, right? So titanium sapphire lasers are really good for these applications because of this high conductivity, thermal conductivity. And they are also ideal for either widely tunable lasers, because we can select any wavelength from this wavelength range that is given here, or for ultra short pulsed lasers, because I will talk about that on the next lecture maybe, but generally if you want to build a pulsed laser and you want to have the shortest possible pulses, for example, femtosecond pulses, then you need a broad bandwidth, because the pulse duration is directly connected with the bandwidth. So there is a so-called time bandwidth product. Which means that the product of the spectral bandwidth and the pulse duration is constant. So when we want to have a shorter pulse, we need to have more bandwidth. This is from the relation from originating from the uncertainty, Heisenberg uncertainty, right? So if something is short in time, it needs to be brought in the spectral domain. So since these lasers can have a really broad emission spectrum, they can also emit really short pulses. And it turns out that these TISAF lasers, they have the strongest absorption line in the green wavelength region. So they can be pumped at the wavelength of 532, which can originate from a neodymium laser with second harmonic generation. So this image shows you the absorption and emission of titanium sapphire crystal for 2 different polarizations. So these pi and sigma are polarizations, but let's just look at the pi polarizations. You can see that we have the maximum here around 500 something, which means that if we have the laser at 532 nanometers, we are almost in this in the peak of the absorption. So it means that the second harmonic generation of the neodymium laser almost ideally matches the absorption bandwidth of maximum of titanium sapphire. And you can also see with the brown color here the extremely broad spectrum of emission. So the peak is around 800 nanometers, so we will have the highest power at around 800 nanometers. So that's why most of the titanium sapphire lasers have this central wavelength. But basically, we could choose any wavelength from this entire spectral range if you want to build a titanium sapphire laser. Interestingly, you might know also from jewelry that sapphire it's a really nice blue crystal which can be found in any kind of jewelry, and titanium is a metal which has a typically just a metallic color. But if we dope sapphire with titanium, the crystal is red for some reason. And once again, you can buy these crystals in the form of rods, or just cubes or discs or any shape you want. Titanium sapphire lasers are also available commercially, of course, and they can be purchased from many manufacturers. But what is important in TiSAF lasers is that if you open this kind of titanium sapphire laser, you will always see a lot of green light because there is the pump which is green, right? So this is most likely a second harmonic generation from the neodymium lasers. So a lot of green color, and then the green light is focused on the sapphire crystal, which is somewhere here, and the titanium sapphire then emits its own wavelength between 700 and 1100. Yeah, so this is a typical setup of a titanium sapphire laser, but this particular laser is a pulsed laser, so it generates these femtosecond pulses. That's why there are two prisms, P1 and P2. These are prisms, optical prisms that are used for filtering and inserting dispersion. But what is important here, what you can see here, is that this titanium sapphire crystal is placed under an angle with respect to the optical axis. So someone might ask why we don't just put this crystal like that and we just have light propagating here. Because of these reflections from the side surface, because the refractive index of titanium sapphire is quite high. That's why these walls of the crystal are cut with respect to their Brewster angle. So you remember the principle of the Brewster angle, which was used in also gas lasers for ensuring linear polarization. So the same applies here. So the crystal is usually cut at this Brewster angle, placed at this Brewster angle. So the light incoming to the crystal goes here, and then because of refraction, because of the difference of the refractive indices, is guided this way and then exits this way. And by that, we just ensure that we have no reflections from this surface, but all the light is just refracted inside the crystal. And you can see that it is pumped within a solid state laser at 532 nanometers. In this case, this was at the power of 5 watts. And interestingly, as I said before, these lasers can be used for generating of very short pulses. We will talk about pulsed lasers on the next lecture a little bit, but you can already see that if we just exploit the entire gain bandwidth of the titanium sapphire lasers, so from 600 up to even 1200 here, this spectrum can support really short pulse generation at the level of 4 femtoseconds in this case. So this is a really, really short pulse. And this can be done only in TiSAF lasers because of the availability of this very broad bandwidth. I have a movie that shows the TISAF laser from I hope you can see it, but here you can see the green pump that is focused on the titanium sapphire crystal, and the titanium sapphire crystal generates the red, which corresponds to the, let's say, 800 nanometer bandwidth, and the pulse is bouncing between the mirrors of the resonator and going to the output. Okay, so final type of lasers for today are disk lasers. So disk lasers are kind of a modification of solid state lasers. So the active medium is formed as a very thin disk. And the disk is very thin, so the thickness is at the level of, let's say, 100, 200 micrometers. And the area can be quite large. So the size of the disk can be few millimeters up to even few centimeters, depending on the applications, but only hundreds of micrometers thick. So what is the goal of that? So the main idea behind this is that if we have a crystal, let's say neodymium doped crystal, which is just a bulk cube of material, and we focus light into this crystal, focus the pump inside the crystal, right? Let's say that we have it here. So we induce a lot of heat focused just exactly inside, in the middle, inside of the crystal, in the middle of the crystal. So we accumulate a lot of heat in a very tiny spot. And usually if we want to cool this crystal, then what we can do, we can just put some heat sinks, or we can just extract the heat from the side walls, right? So we just extract the heat from the side walls of the crystal. So it means that we just induce a gradient of the temperature because we will effectively cool only the side walls, but we heat the middle of the crystal. So it means that we have a thermal gradient. So we induce a lot of stress into the crystal. So when we put too much power into this kind of crystal, it might damage, because it might either break or we can burn a hole in this crystal. So to avoid that, we are using disk lasers, because if the disk laser is thin enough, we can easier extract the heat from the disk, because we can place the disk on a heat sink, which can be water cooled, because we have a huge surface of the disk. So it's much easier to extract the heat from the surface, from the side, than from the inside of the material, right? So if we minimize this, one of the dimensions of the disk, of the medium, so this is on the range of micrometers, we can effectively remove the heat from the back side, right? So by doing that, we can easily scale the output power of this kind of lasers up to even kilowatts. So as far as I remember, there is a, I think, 16 kilowatt laser available on the market, a disk laser. So they enable a really high power extraction because of efficient heat removal. Usually they are based on ytterbium disks, or also sometimes neodymium, but usually crystals doped with ytterbium. So ytterbium is another lanthanide, rare earth ion, and ytterbium is also a 4-level system. So ytterbium is pumped at the wavelength of 976 nanometers and has the emission at the wavelength of, let's say, between 1030 and 1080 nanometers. So it has a quite broad emission bandwidth. So pumping of these disk lasers is also something which is not so easy because these disks are placed on the heatsink on one side, right? So so the disk is always on one of the ends of the resonator. So usually these disk lasers are pumped in so-called these two mirrors, and the pump is following a completely different path than the signal. So the signal is the green light, the signal emitted by the laser, and the red one is the pump. So this is the so-called multi-pass pumping. Yeah, this is another image that shows this arrangement. So you can see there is the disk here inside, and the disk has the thickness of about 100 micrometers. The disk is placed on the heatsink, which is also at the same time a reflector, a mirror. And this heatsink is water cooled, so you have water channels inside. So we just extract the heat very efficiently. And the laser beam is the red one here, and the green one is the pump laser in this image. So usually you have a hole here in this parabolic mirror, which is just the output aperture for the laser light. And I have another movie. I assume that it will maybe, I think, yeah, the important part of the movie is here. I don't know if it's lagging through Zoom, but I think that yeah, you might. Yeah, I can send you the link if it's lagging, but if
it's
not,
okay.
Okay. Yeah, so this is the guy is talking something. This is the crystal. This is the disk. Yeah, and the disk is placed on the heatsink. So this heatsink is a reflector, and the system is surrounded by the set of these parabolic mirrors. And then the pump light is injected from the side, and you see that it bounces between these mirrors and hits the
hits the disk several times. So it is somehow, let's say, recycled, right? And the resonator is between the disk, the surface of the disk, and a back mirror here at the output. So since this mirror, the back mirror is partially reflective, then the portion of light is extracted from the laser. And this is another movie that shows a product done by a company Trumpf, which is one of the biggest manufacturers of disk lasers, and you can see how compact the construction actually is. So there is this disk inside, and of course the multipass pumping, and two different outputs from the laser. And it fits one box with a very small footprint. So this is just connected to the water supply. And this kind of lasers are widely used in the industry for, yeah, as you can see, some manufacturing of components, cutting, welding, and so on and so on. So generally in industrial applications. Okay. Do you have any questions? Okay, if there are no questions, so everything was clear. That's all for today. So on the next lecture, I will talk about pulsed lasers. And I think it's next week, I think, or if something changes in the calendar, I don't remember. Okay, so thank you and see you